Section 12 contains a couple of unrelated topics, which, neither one of them was worth a whole week. Well, actually, I could spend more than a week talking about gravity, but it's a topic we'll return to in Physics 132. There are some ways where it seemed convenient and efficient to me if we talked about gravitational fields and electric fields at the same time. So more to come, but to go through at least some things about gravity. Gravitational attraction is a universal property of matter, okay? Every mass attracts every other mass, kind of as if everything in the universe were connected to each other by rubber bands. In a classroom where there's people sitting here in the usual rows of desks, you'd be attracting the people closest to you with a force somewhere around 10 to the minus 7 newtons. The ones on, across the room would be more like 10 to the minus 8 newtons. So where did that number come from? Well, one way that gravity is not like having everybody connected to everybody else by rubber bands is the force does not obey Hooke's law. It's a whole different type of behavior. Let's say you've got two masses. M1 and M2. This could be the Earth and the Moon. If it's going to be you and the person sitting next to you, then this is only going to give an approximate estimate of the force, once I get it written down, because I'm assuming here, well, either point-like masses, or if the masses are spherical, then they behave as if you had a point mass located at their center, okay? But you get a more complicated shape like a human being. Newton's inverse square law will only work exactly if they're far enough apart to consider them to be point-like. But if you have two people that are standing just a few feet apart, things get more complicated. Anyhow, the centers of these two objects are for radius, perhaps the radius of the moon's orbit. They attract each other with some force F. This is an example of Newton's third law. Number one attracts number two pulls back on number one. They pull on each other, equal and opposite forces, okay? So, as I said, we're assuming here point masses or spheres. The direction of the force is the way I've indicated on the diagram here. Each force points directly toward the other mass. For the magnitude of the force, M1 and M2 are the two masses. R is the distance between their centers, as I've shown on the diagram. G is a universal constant. Capital G is not to be confused with little g, 9.8 meters per second per second. Little G is the strength of the gravitational field that we happen to be standing in here, or maybe you're sitting down. Little g varies depending on where you are. Slightly between different places on the Earth, significantly if you go different places in the universe. Capital G, on the other hand, is one of those things like the gas law constant, or there's a bunch of constants like that. A universal constant means it's the same everywhere in the universe, all times, all places. As long as you're measuring in SI units, it's going to equal about 6.67 times 10 to the negative 11, which of course is something you can look up on your reference handout. There's a whole glob of units on that number to make the force come out in newtons. Measuring this number is the topic of lab number 12, which actually some of you have already done because we've only got 3 setups, so half the class does it while the other half is doing lab 10. But just to review that, especially for the half of you who haven't done it yet, the way it works is that with a very sensitive balance, we measure the force between known masses that are a known distance apart. So you determine everything in this equation aside from capital G, and you can solve for it. Isaac Newton, by the way, made a great philosophical advance by saying, you see, if you go back into the Middle Ages or earlier, the earth and the heavens were thought of as distinct places, each of which had their own separate set of rules, okay? Well, Newton, this is one of those stories like George Washington cutting down the cherry tree. It may not have happened exactly this way, really, but supposedly Newton was sitting in his mother's garden one day thinking about, now what would provide the centripetal force to make the moon orbit around the Earth? I mean, it is a historical fact that he was living at his mother's house for a while because the plague had come to London and everybody had left town to go live with anybody they knew who lived out in the country. So Newton spent something like a year and a half waiting for them to reopen the university and did some of his most significant work during that time period. But anyhow, he was sitting there thinking about that. What provides this force? And all of a sudden, supposedly an apple fell from the tree over there. And he goes, oh. And, you know, I mean, it's just a little equation, but the philosophical point is that it's the same force that makes an apple fall from a tree on Earth that also pulls on the moon up there in the heavens, making it circle around the Earth. Universal gravitation. So it's time for a short example. Well, it's not that short, I suppose. Section 12, problem 1. From the following information, find the acceleration due to gravity at the moon's surface. Something that was known a long, long time before anybody actually went up there and dropped something to see how fast it fell. So that goes like this. Compared to getting to the moon, it's a pretty simple, straightforward calculation. Where's the best place for this? Well, we're going with that. So let's say you're an astronaut and you're standing on the moon and you've picked up a rock. I hear there's a lot of them up there. And so you drop the rock and here it is on the way down, or actually could still be in your hand. It doesn't make any difference. Whether you're holding it or whether it's falling, that rock is attracted to the moon with the force that we call its weight. Weight, as we have seen many times, is equal to mg. And the reason I put the subscript on g is that this would be not 9.8, but g on the moon, which is the thing the question asks for. Find the acceleration due to gravity at the moon's surface. Now, gravity, like any force, is a mutual interaction. Not only does the moon pull on the rock, but the rock pulls on the moon with the same amount of force. And this picture here is really just this picture here all over again, except here I drew them both about the same size, and here one thing's a lot bigger than the other one. But it's a picture of two objects pulling on each other gravitationally. So this force is given by Newton's inverse square law that I wrote over here. So gravitation constant, m is what I called the mass of the rock. M sub m, that's the mass of the moon. And the distance between their centers would be the radius of the moon. I mean, the size of the rock is negligible. So if it's at the surface of the moon, its distance from the center of the moon, remember, r here is the distance between their centers, that would be equal to the radius of the moon. Now, these things were given in terms of the mass and radius. Well, I guess something else I should do first. I have here two different expressions for the same force. Okay, the gravitational force equals m times little g. The gravitational force equals this thing I've written here. So our test mass, the mass of the rock, cancels out. Divide both sides by m and it's gone. And you're left with g at the surface of the moon, the thing we're looking for, equals capital G times the mass of the moon over the radius of the moon squared. This, by the way, says this in parentheses just below the question there on the handout. You can determine the mass. Here I'm going to use the mass of the moon to find the value of G, but you can turn it the other way around. Say you wanted to know the mass of the Earth. Well, put M's here for Earth instead, or E's for Earth instead of M for moon. The mass of the Earth would equal G for the Earth, which we measured in one of our labs, and I recently talked about another way of measuring it with a pendulum, so that's easy to measure. G times the radius of the Earth over the gravitation constant would equal the mass of the Earth, so that's why measuring the gravitation constant is sometimes called weighing the Earth. That being this week's lab, like I said. Anyhow, filling in what was given in the question. mass of the moon, 0.0123 times mass of the Earth. And what most people I have found would do at this point is they go into the formula sheet and they look up the mass of the Earth and they look up the radius of the Earth, which are a couple of large cumbersome numbers. But if you put those, and also the gravitation constant, a small cumbersome number, and you put them all in there and you punch it up and that gives the right answer. Or the way I would look at it is let's collect all those constants together, 0.0123 over 0.273 squared, and put all the letters together. G times the mass of the Earth over the radius of the Earth squared. And the reason I thought that would be a good idea is because if G, little g, is capital G times the mass of the planet over the radius of the planet squared, this would be little g for the Earth. So instead of three cumbersome numbers to plug into that, you've got just 9.8 to stick in for this. That divided by this squared comes out 0.165. I could put in 9.8 for that, but actually what's probably the most meaningful thing for most people is to just leave it as a comparison to what they experience on the surface of the Earth. One-sixth is almost equal to 0.165. So just saying, giving the answer in G's rather than in meters per second squared is probably a good way to do it a lot of times. On the surface of the moon, you would experience 1/6 of the gravity that we have here in this room. Let's see. Yeah, actually, it wasn't really worth moving the camera over there just to point you at where it says two words, Kepler's laws. We'll just kind of point it at the blackboard. Kepler's laws are the basic principles that the planets obey as they, well, not only as planets orbit the sun, but satellites going around the Earth or anything like that. The motion of the planets was one of the earliest scientific questions to attract attention. There are observations going back to the ancient Egyptians and Babylonians and almost as far with the Chinese. The ancient Greeks were the first to explain the observed motions with some kind of a model. You have there the beginnings of something almost kind of sort of not quite like science with the ancient Greeks. Earlier people just had empirical patterns. It's like, well, this planet is next to that planet every however many years. And so probably in the future, it'll keep doing that. 11 years from now, it'll be next to this one because 11 years ago it was, and now it is. The Greeks pictured the Earth, which, by the way, the ancient Greeks knew was round. It is, some people think Christopher Columbus discovered that the world is round. Actually, it's kind of the opposite. Columbus didn't sail west out of Spain due to some brilliant insight. Columbus did that because he made a mistake. He thought the world was smaller than it actually is. So he thought it wasn't all that far to get to China and India in that direction, when in fact it would be like halfway around the world, even if this continent hadn't been in the way. But the ancient Greeks actually not only knew the world was round, they had determined its diameter to, well, there were some measurements that were only off by a few hundred miles, actually. But you had the Earth, you had the planets all orbiting around the Earth. It was kind of a complicated system, which I don't need to get into the details of because it turns out it was wrong. But in 1543, along comes Nicholas Copernicus. Of course, Copernicus was Polish, okay? Copernicus is not a particularly Polish-sounding name, you may have noticed. But back then it was fashionable to kind of Latinize your name. It always sounds better if you pretend you're a Roman, I guess. Same thing with Columbus, you know. To the Spanish, his name was Colon. To the Italians, his name was Colombo. But we all know him as Columbus because that's what people did back then. You made yourself, you Latinized the name. Anyhow, 1543, Copernicus proposes that the planets orbit around the sun, including the Earth. He made the Earth into a moving object going around the sun like the other planets. This was at the time fairly unimpressive because if, let's say you try to predict where Mars is going to be 2 years from tonight, if you use the system that Copernicus devised, you'd get it pretty close, but you'd be off typically by a few minutes of arc, not minutes of time, 60 minutes to a degree. Well, if you used the book that Ptolemy had written 1,500 years earlier and tried to predict where Mars would be two years from tonight, it would also be off by just a couple of minutes. So why would you abandon what everybody has believed for a millennium and a half to look at it this other kind of suspicious sounding way? And so Copernicus's idea just kind of laid around, and people didn't pay too much attention at first, although by the early 1600s, things were kind of heating up and it was getting controversial. Well, I've already, I think, mentioned how Galileo helped explain what was going on with his ideas on inertia. But at about the same time in Austria, there was this guy named Johannes Kepler. Kepler was not an astronomer. He didn't really spend much time looking at the sky himself the way Galileo did. Kepler was a mathematician. But he inherited a very large body of observational information that was the most accurate anybody had ever compiled up to that point. And he set about sifting through it for patterns. And, you know, you have to kind of admire the guy because, I mean, Newton hadn't been born yet. I don't think Newton's father had even been born yet. So there was no theoretical guidance in what he was looking for. He was just going through all these numbers by trial and error. And over a period of about 20 years, he found some patterns that we now call Kepler's 3 laws. And they go like this. Kepler's laws. Kepler's first law. I'll write it down in a moment, but the general idea is that the path of a planet's orbit around the sun is an ellipse. The reason that Copernicus didn't really create a system that was any more accurate than the ancient Greek, the geocentric model of the ancient Greeks, was that Copernicus retained the classical prejudice in favor of perfect circles. You see, the ancient Greeks weren't really scientists, even though they helped move the world in that direction. They were really philosophers. So the way you would figure out the shape of a planet's orbit goes something like this. They were all about deductive reasoning, okay? I mean, it wasn't like Aristotle never did any experiments, but if you wanted to figure out the shape of a planet's orbit, you would say the planets are located in the heavens. Everything in the heavens is perfect. The circle is the most perfect of shapes. Therefore, the orbits of the planets must be based on circles. Well, circles superimposed on other circles is what it amounted to. And with Copernicus's system, he was able to kind of clean up some of the contrived sounding details, but he was still basing things on perfect circles. And Kepler comes along and he says, I find that the observational data fits best to elliptical orbits. The planets follow elliptical orbits with the sun at one focus. Hopefully you've looked at least a little bit at conic sections in some math course. Whether you have or you haven't, probably I should review exactly what an ellipse is. An ellipse is kind of an oval-shaped curve. The longest axis that you can draw across it is called its major axis. Okay, it passes through the center of the ellipse and also the points that are the most distant from the center. C for center, right there. Half the length of the major axis, in other words, the distance from the center of the ellipse to the most distant point there or on the other side, either one, that's called the ellipse's semi-major axis. And I will have some reason to refer to that before I'm done. I'm going to use the letter A, which is a pretty typical notation for the semi-major axis of the ellipse. To either side of the center are points I'm going to label with the letter F. F for focus. An ellipse is an oval that's drawn according to very specific rules, which can be explained in different ways. But if you don't want to get too mathematical about it, it goes like this. You pick your two focus points, get a couple of nails, drive one into the blackboard there, drive the other nail into the blackboard there. get a piece of string. Tie one end of the string to this nail, tie the other end of the string to that nail. Take your piece of chalk, pull it up against the string, and keeping the string nice and tight the whole time. Well, there'll probably be a couple of places I have to pause for a moment to get the piece of chalk, like, would get caught on the strings that get caught on the nails and things. But aside from little details like that, just run it around, keeping the string tight the whole time, and it'll draw an ellipse. In more mathematical terms, what that means is for any point on the ellipse, like this one right here, the distance from that point to the one focus plus the distance from that point to the other focus always adds up to the same constant, the length of the string. Okay, so that's what an ellipse is. It's an oval shape drawn according to those rules that I just described. As the planets go around the sun is not located at the center. That's a common mistake I find I have to try and disabuse people of. The center is just a point in empty space. There is nothing interesting there. The sun is over here at one of the focus points. The other focus is also empty. There's nothing there. But, as the Earth, for example, orbits around the sun, I've greatly exaggerated the eccentricity of this thing, by the way. If I drew a scale drawing of the Earth's orbit here on the blackboard, you'd have to go after it with a meter stick to see that it wasn't a perfect circle. It would not be noticeable just to the eye. When the Earth is here, it's about 91 million miles from the sun. When it's over here, it's about 95 million miles from the sun. So it varies as it goes. Some of the other planets have more variation than that, but so that's first law, elliptical orbits with the sun at one focus. Second law finishes demolishing the idea of uniform circular motion for the planets. First law got rid of the circular part. Second law gets rid of the uniform part. The planets speed up and slow down as they go around their orbits, okay? Fastest when it's closest to the sun, slowest when it's farthest away. That is kind of like, if you think about it a little bit, kind of like common sense from a modern point of view. But remember, gravity, universal gravitation was many decades in the future at this point. Kepler had no explanation for why this should be true. From a modern point of view, it's just, if the sun is here, if you get a planet heading out this way, so it gets farther and farther from the sun, well, what happens if you throw a ball up in the air? As it gets farther and farther from the Earth, it slows down. And on the way back down, as it gets closer and closer to the Earth, it speeds up. Well, the planets do the same thing. If they're moving farther from the sun, they slow down. If they're approaching the sun, they speed up. Exactly how the speed changes is described by Kepler's second law. Line from the sun to the planet line from the sun to the planet sweeps through equal areas in equal times. So this often gets called the law of equal areas. I should illustrate this with a picture. So here's our elliptical orbit once again. Again, the eccentricity is greatly exaggerated for any of the major planets, although you get comets that move along orbits that are this flattened, or even more so. But let's say this is the sun over here. And maybe this is Mercury, the planet Mercury, following this orbit I've drawn. So at one particular moment, the planet Mercury is there. And a week later, it's moved along its orbit and gotten to here. So there to there, 1 week. Okay, well, a month and a half later, something like that, Mercury's over here on the other end of its orbit. At one particular moment, it's here. A week later, it's over here. So, equal times. A week to get from there to there, a week to get from there to there. If you draw a line from the sun to the planet, that line during that week sweeps through a certain number of square miles, kind of like a windshield wiper going across your windshield. How many square inches does it sweep through? How many square, whatever your favorite unit is, but how much area does that line sweep through? I'll call that A1. And over there, the line from the planet to the sun sweeps through an area A2. And what the second law says is that the short fat area, A1, includes the same number of square miles as the long skinny area, A2 does, equal areas in equal times. So when this line is long, the planet goes a short distance in a week. When the line is short, the planet goes a greater distance in a week. Planet moves fastest when it's closest to the sun. It moves slowest when it's farthest away. And this statement describes exactly how its speed changes. Third law. Probably work better if I moved the camera, wouldn't it? So Kepler published his first two laws in, I want to say it was 1609. Maybe I'm off a year or two in that. Took him another 10 years to come up with the third law. The third law looks at how the orbital period of a planet compares to its, well, the phrase that's used when you're talking to just the general population is you call it the average distance from the sun. What it really means is the semi-major axis. Remember back over here, I drew this little ellipse and I labeled this thing A, half the length of the major axis of the elliptical orbit. So closest planet to the sun, Mercury, gets all the way around in just 88 days. Here in the number 3 spot, it takes us a whole year to get around once. Jupiter takes 12 years to complete one orbit around the sun. Pluto, whether you call it a planet or not, any object orbiting the sun obeys Kepler's laws. Pluto has an orbital period of just under 250 years. It's only been a third of the way around since it was discovered in the 1930s. So what's the pattern? How does the orbital period, clearly greater distance from the sun corresponds to a greater time per orbit, greater period, but what's the exact relationship? Well, what Kepler was eventually able to see was that it's actually, in the system of units usually used by astronomers, it's just t squared equals a cubed, like I started to write down there. But if you're going to work with, for example, SI units, there would be a proportionality constant involved that's not 1. Astronomers have a system of units rigged up where the proportionality constant would just equal 1. But in this course, we pretty much stick to SI units, so I'm going to make it t squared is proportional to a cubed rather than saying equals. T, capital T is the same thing as when I was talking about vibration. It's the period. And in this case, the orbital period. And A is a semi-major axis of the orbit. In the special case of a perfectly circular orbit, you don't really get perfectly circular orbits in nature, but you could, for example, with an artificial satellite, you could launch it just right so that you had a perfectly circular orbit. And in that case, this would just be the radius. A would just be the radius of the orbit. You can think of a circle as being sort of a degenerate ellipse, an ellipse whose eccentricity is 0, so that the major and minor axes both have the same length. And so both focal points are located at the center. So early 1600s, Johannes Kepler comes up with the stuff I was just describing. So then a number of decades go along and you get to the late 1600s. And as I probably mentioned before, along comes this guy, Isaac Newton, who takes these various discoveries of the people who went before him, Galileo, Kepler, and so on, and kind of weaves them all together into a complete description of the mechanics of the world. So one thing Newton accomplished was he was able to explain Kepler's laws from deeper principles. Those deeper principles being, his 3 laws of motion, F equals ma and all of that. Also his idea of universal gravitation. In Kepler's time, his laws were just empirical relationships. It's like, well, I don't know why it's true, but I look very carefully and that's what all the data shows. So Newton was able to explain it all and in the process, he was also able to generalize it, because Kepler's laws, as originally stated by Kepler, applied strictly to bodies orbiting the sun. When Newton got through with them, anytime you've got two bodies, whether it's the Earth orbiting the sun, whether it's the moon orbiting the Earth, whether it's a binary star system where the two stars are going around each other, he generalized it to cover all of that. And I'm not going to go into a great deal of detail, but just to kind of give you an idea, I'm going to write out how to derive Kepler's third law. It's only a few lines. If you assume the special case of a perfectly circular orbit and a few things like that. So Kepler's three laws were later derived and explained by Newton. For example, the third law. So as I said a moment ago, I'm going to just look at a special case so I can keep it short and sweet. One of the assumptions I'm making that's not completely general is I'm going to assume a perfectly circular orbit. The other assumption I'm going to make is that M1 is many, many times more massive than M2. What that does is it allows me to consider M1 stationary, okay? If you, for example, have two identical stars, they both orbit around, if the stars are identical, their center of mass is halfway between them. Wherever the center of mass is, both of the stars orbit around the center of mass, kind of like this. Even with the Earth and the moon moves around, or the Earth moves around in the moon's gravitational field, as well as the moon moving around in the Earth. The Earth being, we just saw in the other example a few minutes ago, the Earth is almost 100. It's like, the Earth is like 80 times as massive as the moon. So the center of gravity, or the center of mass, is a lot closer to the center of the Earth than it is to the center of the moon. But it's, you still get the Earth kind of going around in a little circle as they both orbit their center of mass. But, you know, if this is Jupiter, and if this is a paperclip, you don't really need to worry too much about how Jupiter is orbiting around the system's center of mass. You can say that thing sits still, okay? So we're assuming a very lopsided mass distribution like that. That way we can think of just one object moving instead of both of them. That and circular orbits. So as this thing circles around that, it is gravity that provides the centripetal force. Gravity is the force toward the center that makes the little mass circle the big one. The force of gravity is given by Newton's inverse square law. If it's going to be a circular orbit, just like any other time something is moving in a circle, This, this force toward the center, the centripetal force, has to equal mv squared over r. That would be m2 because that's the one that's going around in a circle. Okay, well, once you've got that written down, m2 cancels m2. Also, this r cancels one of the two r's that you have over here. And you're left with v squared equals gm1 over r. Now, if we're going to have an expression that involves the orbital period, I need to make a substitution. So the speed of the planet, on a circular orbit, the speed would stay perfectly constant. The speed of the planet, well, in general, speed is distance over time. That's the definition. The planet would cover a distance equal to the circumference of the orbit in a time equal to 1 period. I mean, that's what the period means, is the time to go around the orbit once. And the distance to go around the orbit once is 2 pi r. So we have for v, we have 2 pi r over t. So I can say that g times m1 over r equals 2 pi r. 2 pi r over t is the speed. We have the speed squared there. So let's rearrange a few things. Get rid of denominators. You know, who really likes fractions when it comes right down to it? So I've got a t squared here. I'm going to multiply both sides by t squared. Over here, I've got after you square it, it would be 4 pi squared. Get that part written down. And then I've got an r squared here, which I can combine with this other r. Gives me an r cubed. And then it's kind of handy to combine all the constants in one place. I'm going to divide through by g and by m1. And there's the third law, Kepler's third law. T squared is proportional to, well, in an elliptical orbit, I said a cubed, but like I said, in the case of a perfect circle, the semi-major axis would just be the same thing as the radius of the circle. So square of the period, cube of the distance from the sun, and this thing in parentheses is the proportionality constant. Now, if you want to generalize, get away from all these assumptions I made, what if M2 isn't much smaller than M1? What if they're similar masses so that both of these things are in motion? And what if it's in an elliptical orbit, an ellipse with a non-zero eccentricity? So it's not a perfect circle. Well, actually, it doesn't look terribly different. I'll write it down here. So for the general case, where M2 is not a very small amount of mass, and where you have an elliptical orbit, this is the version that's on your formula sheet. If it's not a perfect circle, then where I had the radius of the circle in this special case, that becomes the semi-major axis of the elliptical orbit. And if you allow both masses to move around, where I had M1, you have the total mass of both of them, okay? Where, if this is Jupiter and this is a paperclip, well, the mass of Jupiter plus the mass of a paperclip equals the mass of Jupiter, unless you're going to like 30 significant figures or something. So M1 plus M2 reduces down to M1 if M2 is very small. But in the more general case, it's the total mass. And aside from that, it's the thing that I had written up here. So that's Newton's generalized version of Kepler's third law, so that it now applies to any sort of two-body system. As for the other two, I'm just going to, without going into the details, second law remember, the second law was the law of equal areas, about how the planet speeds up and slows down as it goes around its orbit. It turns out that once you get into the details and start analyzing all of this, Kepler's second law is equivalent to conservation of angular momentum. In 1609, nobody had ever heard the phrase angular momentum, but looking back at it from a modern point of view, the law of equal areas is just a different way of looking at the same basic idea that we now call conservation of angular momentum. So second law is equivalent to conservation, I abbreviated conservation, equivalent to conservation of angular momentum. As for the first law, the idea of an elliptical orbit, I'm just going to write down that that can also be proven from Newton's laws of motion. Just as a little footnote to the first law, when Newton generalized that, what he ended up saying is not that one object moving through another's gravitational field necessarily follows an elliptical orbit. It became a conic section when Newton was done with it. If the object has too little energy to escape from the solar system, or whatever it is it's orbiting around, then you have an elliptical orbit. If it's exactly at the escape velocity, then it will have a parabolic orbit, an open-ended orbit where the thing never comes back. And if it's above the escape velocity, you'll have a hyperbolic orbit with the sun at one of the focus points. The sun is always at the focus of whatever kind of conic section you're talking about. So I've got a couple of examples, and then that would be a good place to take a break between the two different topics that I've got in this unit. And gotta raise that up a little bit. Okay, so something to point with. Example number 2. I didn't fill in any exact numbers, but this is supposed to be the path that some object follows. There's some comet orbiting around the sun, or some object like that. And at one, you don't have to know all the astronomy jargon, but if anybody's interested, P stands for perihelion, A stands for aphelion. Perihelion is the closest point on an orbit to the sun, or if it's the same prefix as if something orbits around the Earth, then it's perigee and apogee. If you've got something orbiting around another star, it's periastron and apastron. Anyhow, that's what the P stands for. Perihelion and the A is for aphelion. So if you knew both of these distances and you knew the speed with which the planet passes perihelion, how fast is it going over here at the other end of its orbit? Just in terms of these other letters is the way we're going to leave it. Well, really? This is not a new example. Kepler, I mean, this is Kepler's second law is the thing that's relevant here. But like I said up here, this is the second law is equivalent to conservation of angular momentum. And toward the end of section 9, I think it was, I did that example where I was spinning the cork around over my head, and then I pulled the, well, I guess you can't see me down. Yeah, okay. Anyhow, I pulled the string and I made the radius get a lot shorter. And as the cork came in closer to my hand, it went around faster and faster and faster. This is the same example all over again, except the numbers are a lot bigger, okay? I mean, the cork was 30 or 35 grams, something like that. Now you've got a planet, but, and the distances are a lot bigger too, but that doesn't make any difference. It's exactly the same principle. So, number 2. The angular momentum that the planet has as it passes perihelion is equal to the angular momentum that it has as it passes aphelion. Now, never mind all this stuff about figuring out the areas of the elliptical sectors, the way that Kepler originally stated his law. It's conservation of angular momentum. Angular momentum is the moment of the momentum, R times mv. So R times the momentum at the one point equals R times the momentum at the other point. The mass does not change. The planet doesn't become more massive or less massive as it moves around its orbit. So I can divide both sides by m, and that leaves me with a trade-off, an inverse proportion between the radius and the speed of the planet. So solving it for VA, which is what the question asks me to do, In that example from section 9, 1/3 the radius gave you 3 times the speed. And that's all there is to this. One more example on Kepler's laws, this one with a little more meat to it, I guess. Actually, maybe I should point you over here for a moment first. Kepler's third law, as originally stated by Kepler, was just something that was kind of interesting. But after Newton got done with it, it contained the total mass of the 2 bodies that are orbiting around each other. This provides astronomers with an extremely useful tool. This is how you weigh a star, or a couple of stars, actually. If you have just a solitary star just sitting there in the sky all by itself, there is no direct method for measuring its mass. We've learned enough about stars that you can infer what its mass must be from its other properties, but as far as actually measuring mass so that you learned what those correlations were in the first place, the only way you can weigh stars is if they occur in a binary system. Fortunately, binary systems are extremely common. Something like 1/3 of all star systems are binaries. So what you do is you watch the thing for long enough that you can tell how much time it takes for the stars to go all the way around once. You know, a little bit of patience, mark a few things on the calendar, and you know the orbital period from watching it for a while. You also have to know how far apart they are. Well, you can directly observe that also, especially if the stars are wide enough to be visually resolvable, but there are other ways of determining the separation also. So you can observe this, you can observe that, the rest of it's fundamental constants. You can solve for the total mass of the 2 stars. How much of the mass belongs to each star? Well, you can tell that from how far each star is from the system's center of mass. The center of mass is closer to the heavier one by an amount that depends on how the 2 masses compare to each other. But that goes beyond what this question asks for. The question just simply gives you the period, separation, and asks you what's the total mass of the 2 stars put together. Okay, so that's the idea behind number 3 there. You've got a period of 14 years, and it gives the separation. Find the total mass, meaning M1 plus M2. So I didn't bother to write out, only be a couple lines anyhow, but I took this thing here and I solved it for the thing the question's asking for. M1 plus M2 equals, I multiplied both sides by the total mass. I divided both sides by t squared, and it gave me this. So once you realize that's what you have to do, it's just sticking numbers in. But they are kind of ugly, cumbersome numbers. I have found like there's a question like this one that comes up on the quiz sometimes, and people have a tendency to make arithmetic mistakes when there's a lot of, twice as many buttons to push, means you're twice as likely to push one of them wrong. And so anyhow, be careful of the arithmetic. We've got 4 pi squared over the gravitation constant, 6.67 times 10 to the negative 11th power. A is the semi-major axis of the orbit, the average distance, if you'd rather say it that way. Think of it as being A for average. 9.5. Now, the distance was given in kilometers. Don't forget to convert to meters. 10 to the 8th kilometers, 10 to the 11th meters. The period, capital T. 14 years. Well, there again, a year is not an SI unit. We have to have the period in seconds. Number of seconds in a year. I'm pretty sure it's something you can look up in the conversions table on the last page of your formula sheet. It's not that hard to figure out. This would be 60 times 60 times 24 times 365 and a quarter. And, or actually 365.24 if you really want to nitpick. So that's the setup. If you can manage to push all the right buttons. It's a big number. Stars are heavy. And again, that's the total mass of both of them. A little further analysis would be required to figure out how much belongs to each individual star. So from here, the rest of section 12 goes off in the direction of looking at the ideal gas law. This is something some of you may have already seen in a chemistry class. This is one of those places where chemistry and physics kind of overlap, where the chemists think it's chemistry and the physicists think it's physics, and we both cover it just in case somebody didn't take the other course. So in the second recording for section 12, we'll do that.